In this paper, we introduced a dual motor actuator along with its impedance control strategy, designed to mitigate collision forces during human-robot interaction. This approach enhances the response performance of cobots. We introduce a kinematically redundant actuator. We call it dual motor actuator or DMA, which comprises of two motors, the sun motor and the ring motor. These motors are connected to a differential, the components of which are illustrated on the right. The DMA has three input options: rotation of the ring motor, the top motor, or operation of the sun motor. These motors can be operated in conjunction to either increase the output handle speed or decrease it, depending on whether their motions complement or cancel each other's effect on the output speed. An interesting behavior of DMA is that during a sudden stop of the output shaft, the kinetic energy from one motor is transferred to the other. This unique feature of DMA allows for a reduction of collision forces. Let's take a closer look to the mass of a robot in collision. Based on the ISO norm, a simple definition of robot effective mass in collision is payload mass plus half of the moving link mass of the robot. Researchers provided a more detailed definition of this effective mass by defining robot Jacobian, collision point, and collision direction. In this case, considering joint reflected inertia, robot effective mass can be higher than what is presented in the ISO norm. In assessing the importance of actuators' reflected inertia, we turn our attention to the DMA's reflected inertia. In the DMA system, for any given speed at the joint, there are two input speeds to consider, which means the actuator's kinetic energy for a given speed is variable, unlike in a single drive actuator where it is constant. For our analysis, we depicted the specific DMA's reflected inertia with dashed blue lines in the different speed distribution between sun and ring motor. This was then compared with several equivalent single-drive actuators. The results are interesting. Within a certain range of speed distribution, the DMA exhibits less reflected inertia. And in line with the findings mentioned in the reference paper, the minimum reflected inertia of the DMA is lower than each of individual drive terrain in motions. For a given actuator with a link and a payload, we can turn these physical properties to a virtual mass spring and damper in impedance control. A lower virtual mass is desirable, but we have to pay for it with stronger actuators to be able to tolerate high torques generated by motor to shape the desired low virtual mass. We constructed an experimental setup to evaluate the performance of proposed DMA within an impedance control mode proposed in this paper. To simulate human-robot interaction accurately, we utilized the certified pulse measurement setup, which commonly referred to as a PRMS setup. To compare performance of the DMA with a single-drive actuator or STA, we implemented a mechanical lock capable of converting the DMA into an STA by locking the ring gear. In this experiment, the ring gear is locked, resulting in an STA during the collision. The results recorded a peak force of 57 Newton as measured by the PRMS setup. In the second experiment, the ring gear is unlocked, allowing the DMA to function. However, the impedance of the ring gear is set low, so it remains stationary in absence of any collision. During a collision event, the ring gear absorbs a portion of the sun motor's kinetic energy. This results in both a reduction in peak force and a significant reduction in the impulse. In the final experiment, the DMA was fully operational, with the speed distribution between the motors optimized to achieve minimal reflected inertia during a collision. This optimization meant that the robot's effective mass was at its lowest, leading to a slightly lower peak forces in the collision scenario. However, since both motors need to halt from a positive speed, the resulting impulse is higher compared to the previous situation where one motor was already stopped. Final results are promising to have cobots that are safer and can perform quicker with utilizing proposed DMA in their joints. Thank you for your attention, and if you are interested, you can contact with us.